My name is John Heyman. I am a research staff member here at the Institute for Defense Analyses, and it's my pleasure to chair this session for you this afternoon. We've got 3 talks for you, and they all look very excellent, so I hope you're as excited as I am. I'll mostly be transparent. I'm trying to get off the stage as quickly as possible here. I'm just going to give a short introduction to our first speaker, Dhruv Patel, and then hand it over to him. I'm very pleased to introduce Dhruv. Dhruv is a research staff member here at the Institute for Defense Analyses. I think he started last year, if that's accurate. He earned his Ph.D. in statistics from UNC Chapel Hill in statistics and operations research. And he is contributing to a wide range of very important projects here at IDA. He's going to be speaking about federated V&V resource allocation, which is a very important topic to us. Please welcome Dhruv.
Thank you all. I see I've been given the tough task of waking everyone else up after lunch. We will try our best here. We also have a wide variety of different organizations present here, so I'll try to kind of accommodate everyone here. This is work with John, who just spoke, and Dr. Joanna Kapp, and it's really a framework for thinking about federated models, thinking about modeling and simulation, and how we can do verification, validation, and eventually accreditation for those models. So let me just kind of ground everyone here in what I mean by federated models. So let's say you're given a task, you have a ballistic missile, you want to know, hey, does this thing work well in an operational environment? Ideally what you would do is you'd go take that missile, launch it at your proposed target location, you'd have the adversary react to it how you would want them to normally react to it, and you just do this maybe 100 times. And just see how much damage each one did, just to figure it out. You can't do that, as you all know. So what do we do? Right now, what we do is we'll say, okay, we'll test out the boosters, ourselves somewhere. We'll test out the reentry vehicles. We'll come up with some notion of how we think the enemy radar works. And we'll have some intelligence, we'll have some SMEs, tell us how that works, we'll put it together, some kind of simulation. We have all these simulations, and then we just kind of connect them naturally into the whole process, and we make what's called a federation, or what we call a federation of models. And this federated model is just interconnected system of models that we are using to eventually determine how well the system works as a whole. So as you guys know, this can lead to a lot of complications because there's a lot of moving parts, a lot of connected parts, and there's a lot of dependencies. So we want to really understand the uncertainty that arises from using a federation of models. There have been plethora of work on understanding how individual model uncertainty can be quantified, but when you put all these things together, exactly how that uncertainty flows through the federation, we really need a framework to ground that. And let me say that IDA is not the first person to do this. We are not the first people to do this. There have been tons of work in uncertainty quantification for systems of systems that have done this. I will take a network-based approach, and there are people at Sandia who've done network-based approaches. I put 2 of their papers up here. I know for a fact that Tom Johnson over there at IDA is doing something on Bayesian uncertainty propagation for networks. I'm pretty sure Scott over there at JHU APL is also doing something similar. So we're not the first to do this, but what we want to do is put together a framework for practitioners that will help them make the choices necessary for their system. And to kind of get them to start thinking about the pros and cons of each choice they make throughout this process. The DoD operational testing perspective that we are really thinking about here is limited test resources, whether that's manpower, training, number of missiles you launch, all of that stuff. Knowledge-based uncertainties, so goes back to the intelligence-based simulations I was talking about. We don't really have exact knowledge on when an enemy seeker might lock into our reentry vehicle. We're kind of guessing that based on intelligence and SMEs. So how do we stochastically or statistically put that together into the federation? And then the last one is, as we all know, trying to validate that operational realism. Okay. So this slide is kind of just an overview of the entire talk. If you take nothing else away, this slide is the one to take. So the main idea here is you take all of these models and you put them into what's called a network. And so a network here is given by these black dots and the arrows connecting them. So each black dot is a model of mine. And if one model outputs something that is the input to another model, I draw a directed edge from one dot to the next. Okay? And as you can see here, there's kind of a natural flow. Think about if I put water in one of these dots and the water goes down the arrows, right? So the water is the uncertainty, and how it flows through that network is what we're looking for. So our main idea here is 5 steps, and the 5 steps I've tried to put as simply as possible here. The first step is for these models, there's going to be input parameters. We need to figure out what those input parameter distributions are. If you have data a priori, what we recommend is you use that data to fit a statistical distribution and then use that. If you do not have a priori data, for example, intelligence-based models, what we recommend is you work with a statistician and SME and intelligence and kind of sit together in a room and come up with a good statistical distribution or a class of distributions that you're willing to use that you can fine-tune later on. Once you've done that for all of these models, we go to meta-modeling. One of the biggest issues with a lot of simulations is they're deterministic. There's no inherent randomness. If I put in 5 as the input and I get 10 as the output, no matter how many times I put in 5, I'm going to get 10, right? It's very hard to quantify uncertainty in this situation. So what we're going to do is we're going to build a meta model on top of that simulation. So we're going to run that simulation across the input parameter space and then build a stochastic process, a Gaussian process, whatever you want to use as a meta model. And this will let you stochastically or statistically quantify that uncertainty. Once you've done this for each node, you're going to do an uncertainty quantification step. You take that stochastic model, that stats model you fit, pick however you want to quantify the uncertainty. That choice is up to you. Once you've done that, you can use the edges of this network to see how it flows through the network. And then step 5 is based on how the uncertainty has flowed, you can allocate validation resources. Okay? The rest of this talk is pretty much going to be an example that I'm going to, with the ballistic model. I just want to preface, all data is notional, it's toy. Nothing is real, okay? 3 types of uncertainties that we're going to consider here. There's exogenous and there's propagated. So exogenous uncertainty is things that are inputted into your model that were not outputs of another model. Think like if I have a 6 degree of freedom model for my booster, maybe temperature is an input parameter, but temperature I'm just directly observing. However, there is variation in temperature. Even if I'm launching from Alexandria, Virginia every single day, the temperature fluctuates. So there's a distribution of temperature that you have to account for. That's an exogenous uncertainty. A propagated uncertainty is something that arises from connecting models. So there's a gravity model that I have to use to figure out the gravity constraints of where Alexandria, Virginia is and how it launches. That gravity model feeds into my 6DOF or trajectory model. So that is a propagated forward uncertainty. Those 2 types of uncertainties are pretty distinct and there's no overlap, but knowledge-based uncertainties can overlap with these other 2. So you can have an exogenous uncertainty that's knowledge-based or a propagated one that's knowledge-based. Knowledge-based is just something that's pseudo-quantitative. I don't really have data. I don't really know for sure. I just have intelligence, SMEs, somebody's telling me this is how it works, and I'm going with it, right? So the example we're going to use is the ballistic missile example I talked about at the beginning. Each node has two types of inputs. So let me just run through a little bit of it first. So on the blue side, we have the 6DOF model, and that feeds into the trajectory. The 6DOF is 6 degrees of freedoms, the 6 ways that a 3D object in space can move. The azimuth, atmosphere, and gravity models are just, we're going to use those as environmental models. That feeds into the trajectory model. That trajectory model will eventually tell me exactly how the RV has been deployed. RV is the reentry vehicle. And that will feed into the RV model, and that feeds into probability of damage. But that's only one side, that's the blue side. The red side is the more challenging aspect for us. So it starts off with this thing called BMUs, which is the Ballistic Missile Early Warning System. Just think they have a radar set up. At what point does their radar detect that our missile has fired and is coming at them? You know, they have a close-in BMUs, which is like a little bit better, but it only works shorter range. That feeds into command and control, C2. That feeds into an ABM, anti-ballistic missile model, feeds into the seeker, feeds into probability of damage. We're not going to know a lot of the red side, so there's going to be a lot of uncertainties there. But this is what we're working with. And again, completely notional. This is not even realistic. I'm sure some of you know. But so each node is going to have two types of inputs. It's going to have exogenous inputs, given by those little light brown arrows. It's going to have propagated forward inputs, given by the dark brown or dark black arrows. Okay? And steps 1, 2, 3, I'm going to go through what they are, but we have to do them iteratively because we have to build the network up. We can't just have the network and then, boom, plop in the numbers. You have to plop in the numbers iteratively. So you start off with the trajectory, you build up the RV, then you build up probability of damage, right? Okay. So step 1, let's say I'm looking at like the seeker model. How do I exactly come up with those input distributions? If I have a priori data, in the temperature case, I can just look at weather.com and pull up temperature for Alexandria, Virginia for the last 50 years and get a distribution, right? For the seeker, if I want to say, hey, it's going to lock in at about 8 kilometers, I don't know that. Depending on who the adversary is, my intel might be very bad. So how exactly do I statistically quantify that? So let's say your SME tells you, we're 70% confident it's between 6 and 10. That's a lot. That's a lot. So how exactly do you put a distribution on that? Well, what I recommend and what IDA recommends is you sit down with a stats expert and you sit down with intelligence and you sit down with SME experts and you guys decide on what distribution you want to fit. Here I've used a normal. So 70% of the mass is between 6 and 10. But as you can see here, 8 is more likely than 6 or 10. However, your SME might tell you, actually, I think it's pretty flat. It could be 6 or 10 or 8 or 7 or 6, equally likely. Then you'd use a uniform distribution. If they tell you, we're pretty sure it's around the 10 range, not so much the 6 range, you skew your distribution a little bit. One thing we're currently working on is getting together a class of distributions that we can give to SMEs that will provide what we call maximum entropy in these situations. So it maintains as much of the uncertainty as possible, yet it allows a flexible choice of priors. So that's step 1. You figured out the input parameter distributions. You're looking at your trajectory model. What do you do now? You need a meta model because the trajectory model you have is deterministic. So you look at your input space. Your input space consists of 2 separate variables, the propagated variables and the exogenous variables. For that input space, what we recommend you do is a space-filling design. You go across the space and you're going to sample. At each of these X marks, you're going to get the same number regardless of how many times you run it, so just run it once. And then we're going to fit a Gaussian process over this. This is a pretty common way of doing meta modeling with the Gaussian process space-filling design. Curtis Miller over there actually has a very lengthy paper on how exactly to make these choices. You can find that at testscience.org, plug. But this is a choice that we are making here. Again, like step 1, this is a choice. Our paper will lay down the foundations of what choices you can make, what are the pros and cons. And we're only approaching this from a practitioner's viewpoint. I'm not going to talk about what's the pros of the expected second moment. I'm only going to talk about what's the pros of the output of the simulation. So, so let's say you do this. You have a mental model for each of your variables or your nodes. I've been using trajectory. How do you quantify the uncertainty from that Gaussian process? Trajectory outputs a spatial model that looks like a track, right? And how exactly do I say, well, gravity accounts for the 16% of the uncertainty in that trajectory model? This is, again, going to be a choice that you make. The choice I've made here is variance decomposition. I look at the trajectory model outputs, and I can look at the variance, or I can look at confidence bounds around that trajectory, and I can say, well, how much of that variance is accounted for by azimuth? How much of that variance is accounted for by atmosphere? I can decompose that variance down. This is, if you've heard of this, ANOVA-based methodology or sum of squares-based methodology. I'm just really pulling that sum apart based on each one of these. So trajectory, again, completely made up numbers. 6DOF is, maybe accounts for 61% of the trajectory uncertainty, 14% for azimuth, 5% for atmosphere, 3% for gravity. What's left? It has to add up to 1. It's those exogenous input parameters that are being fed into trajectory. Okay. So this is step 3, uncertainty quantification. This is just the method I've chosen. You're welcome to choose whatever method you want, your favorite UQ method. Okay, so I've done this for trajectory, and maybe on the red side I've done this for C2. So here's the example. So I go back to my network, I plop the little edge weights down, and then now that I know what trajectory outputs, I have a meta model for trajectory, I can do that for RV. On the other side, I can do that for ABM. And then I can do that for probability of damage. Right? I'm going to iteratively do those first 3 steps as I go in. The reason I can't just do it for RV from the beginning is because I have to know what the output of this trajectory model is. But if the output of the trajectory model is deterministic, it's not going to help me. That's why I need the meta model. I need the meta model for future steps. Okay? All right. We've gotten here. We did a lot of the hard work. Step 4. How much is 6DOF actually contributing to my probability of damage model? How do I figure that out? Because I used a decomposition that's sort of multiplicative, I can just say, okay, probability of damage, RV contributes 28% of the uncertainty to probability of damage. Of that 28%, 76% is coming from trajectory. Of that 76%, 61% is coming from 6DOF. So I can multiply these percentages and say 6DOF contributes 13%. This is not maybe the best way to do this. This is just an example. There are pros and cons of doing this. One pro is that it's extremely simple to explain, and that's a bias that I've chosen here. But there are much more complicated ways and much more statistically rigorous ways to do this. And this is, again, a choice. You might do addition, you might do whatever methodology you want to use. Again, this is, in the final paper, we will lay out the choices, pros and cons. Okay? You can do this for each one of them. You can table it. To all of you who are counting those numbers right now, don't. They do add up to 1. Okay? So then we can say, okay, what contributes the most to total uncertainty? Which uncertainties are we willing to accept, and which ones do we think we can improve? Right? So 6DOF is at 13%. I would say that we could validate that model, and we could spend some more resources and see if that 13% can be improved. This is a massive disclaimer. Just because it has high uncertainty does not mean it can be improved. There are errors in the real world, and some things until new technology comes about, until new methods come about, we can't improve them. But let's just say we can. Maybe we spend our resources on it. Things like BMUs, maybe I can use an engineering emulator to validate this model, and maybe I can get together with my engineering folks and be like, hey, can you talk to the intelligence SMEs and come up with a better simulation for this? Maybe that's possible. ABM, the seeker, I mean, those are just uncertainties I have to accept. Until new intelligence arrives, there's really nothing I can do. So, given that, maybe I just spend my resources on sick stuff and close in BMUs. And this is, again, under the assumption that high uncertainty has the potential to improve. This may not always be the case. You got to be careful. So make sure you talk to your SMEs and ask them if it's even possible. Okay, so I think I'm pretty good on time. Here's a little summary of my recommended framework. So one was to choose the input parameters, appropriately choose distributions. If you have a priori data, use it. If you don't, rely on SME judgment plus statistical expertise. That's key. 2, space filling designs and whatever meta modeling procedure you want to use. I'll venture a little bit away from Curtis and say, depending on your situation, you might not want to use a space filling design, but we do highly recommend one. So think about it. If you don't know, come to IDA and ask us. 3, quantify the proportion of uncertainty explained in each model. You can use your favorite method. I use the variance-based method. You can use whatever you want. Tom over there prefers Bayesian methods, predictive posterior distributions. You're welcome to use that. 4, network structure. Use that to propagate the uncertainties forward. Your choice in 3 will determine how you propagate that uncertainty forward. Because I used variance, I could use multiplication. If you use something like the posterior predictive distribution, you're going to have to do a lot more complicated math. You should see his paper. It's about to be published soon. Another plug. Step 5, use those to, allocate resources for validation or verification, and hopefully it all makes sense to your SMEs, it all makes sense to your engineers. Double check everything with everyone, because sometimes, the choices we make aren't the right choices in this framework. So you have to be careful. Every system is different. Okay, and just a quick plug on future work. We're coming up with that class of distributions, like I said. Going to try to be a maximizing entropy class. We're coming up with a collection of UQ methodologies that you can use on networks. We're coming up with different ways to propagate that uncertainty. We're going to, again, put that down all in our paper with the pros and cons. And a majority of this is really just to get the practitioners thinking about the choices they're making and how to best allocate the limited resources we all know we have. So, yeah, thank you. Any questions? Yeah.
I think I probably am missing something, but I'm thinking about this adding up to one business and doing ANOVA.
Yeah.
So I'm thinking about the case when you take some nonlinear functions, you're applying some nonlinear function to stable the inputs like gravity.
Yeah.
So if it's really complicated nonlinear, then I have to sort of sort things into bins there and look at what that does. Is that the kind of thing you would do? Is like a general procedure? Because just looking at the correlation with gravity would no longer work.
Yeah. When I use the Gaussian processes here. I mean, when you start doing stuff that's extremely nonlinear, you kind of have to come up with methodology for that process. This is something that we are thinking about, of trying to get a class of choices for each situation. Nonlinearity, as you know, presents a struggle when it comes to that because of the different types. So it would just have to depend on your system and what choice you've made there. Yeah.
So am I right that the only thing that's directly stochastic in all of this is the input parameters? So the input parameters are stochastic, and then when you feed those through the models, then you get stochastic output.
that is not necessarily the case. I don't want to speak precisely on certain models, but like your gravity model might be stochastic. Just depends on what model you're running. For trajectory, you might be using a random spatial model, but for azimuth or atmosphere, it might be deterministic. You know, it really just depends on each node is going to have its own unique properties. Yeah. Yeah.
Very nice talk. Excuse me. I'm curious. I've heard the term federated used in different contexts. So what does it mean in the context of what you just presented?
In this context, I really just mean a collection of interconnected models. So if we think of a federation of states, often used in a political world, that's kind of what I mean. It's just a collection of models that have ties to one another in some relationship. Yeah. Okay. Awesome. Well, thank you.
Thank you, Dhruv.